All right. Hello, everyone. It is 7 p.m. We should start our seminar 5. Today, again, we have lots of things to cover, right? And anyway, let's do a quick review of what we have learned in seminar 4. Okay, so let me share the seminar 4 slides. Okay, yeah. So a quick review. So in seminar 4, basically, we discuss the stationarity of time series, right? So we say if you have a non-stationary time series, it will pose challenges in your forecasting, right? So especially the accuracy and also the reliability of your forecast, right? So and in terms of stationarity, we have actually the strict stationarity and a weak stationarity. Okay, so in this course, we basically focus on the weak stationarity, means the mean and the variance. The mean and the variance are constant. Okay, that do not change. So we say the time series will be stationary. Okay. So we can use uh, ACF and PSAF to identify whether your time series is stationary or not, right? So for stationary time series, usually you can see the ACF decreases exponentially, and they have maybe short-term correlation, right? If you see the ACF decreases very slowly, definitely that's not stationary. And your time series could have maybe trend, right? Because a stationary time series, the data have short-term correlations or a relationship. Okay. So we can use ACF and PSCF to identify, right, whether a time series is stationary or not. And in our package, you can use TS Explore and to identify, to obtain the ACF and PSCF of your original time series. And you can use the TS SCF or TS PSCF to get the SCF and PSCF of the time series. Okay. And if your time series is not stationary, and all your time series have a clear trend, for example, your time series have a linear trend, or quadratic trend, or even a cubic trend, right? You can use a difference to make the time series become stationary. Okay, so if the time series have a linear trend, right? So definitely it's not a stationary because you have a trend, right? Linear trend, or either uptrend or downward trend. Okay, so you can use the first order difference to get a time series, and then check the stationarity of the difference in time series. Okay, if your time series have a quadratic trend, then you can use uh, uh, order 2, right? Difference of order 2 to get a difference time series and then check the stationarity. Okay. So the difference is very useful, manipulation, right? To get the time series to become stationary. Okay. And in terms of the seasonalities in your time series, right, you can use also the seasonal difference, right, to get the stationary time series. For if your original time series, all the values are positive, and then if you see the variance or variability becomes larger and larger in terms of time, you can consider use log transformation, right, to transform the original time series become stationary. Okay. And however, remember when you use log transformation, you must do a back transformation if you do forecasting, right? To the original time series. We can use dsdiff function, log function to get the difference in time series or transform the time series in log through log transformation. So here, stationary refers to you have a constant mean and a constant variance, okay, in your time series. Basically, it is so-called a weak stationary, okay, stationarity. Uh, so if your time series have a trend, either a linear trend, quadratic trend, or even cubic trend, then definitely it's not a stationary. Okay, you can use SAF, PSF to determine. Okay, to determine whether your time series is stationary or not. And if it's not stationary, consider using differencing to get the differencing time series and then become the time to get a stationary time series. But you need to be careful whether you are over differencing your original time series, because over differencing may increase the so-called variability of your differencing time series. The variance will become bigger, right? So you linear trend, first order differencing, right? Quadratic trend, second order differencing, and cubic maybe a third order differencing will be sufficient to get a stationary differencing time series. Yeah, we consider a moving average models. So once you have a stationary time series, you can apply the moving average, autoregressive models, and even AMA models. Okay. So this in order to identify whether your model can be your time series can be fitted by MA model or AR model, we can use ACF and PSF, right? So if your ACF have a clear cutoff after a certain leg, while your PSF have no clear cutoff at certain legs, right? You can consider MAQ model, right? Here you can see if your ACF have a clear cutoff after leg 1, so you will consider it is you can use MA1, right, to model your time series. And but you also look at your PACF, and you can see there are no clear cutoff after certain legs. Okay, so this you can yeah, use ACF, PSF to guide which model will be most appropriate to model your stationary time series. And it is here it is very important. So we need to have in order to use ARMA or ARMA models, we need to have some assumption. First, we need to ensure that here in terms of moving average models, right? This is a moving average MAQ model, right? And here we will assume that this epsilon t follows so-called white noise, right? So they are random variables with zero mean and constant variance, and they are normally distributed, and they are independently distributed, right? This is called the white noise. And yeah, this is a MA1 process. You can see this is a ACF. So MA1 process, the ACF will have a cutoff after leg 1, right? For all the other legs, and the ACF will be theoretically 0, right? And this coefficient, remember when we model MAQ process, here we use minus, right? Theta 1 times epsilon t minus 1, theta 2 times epsilon t minus 2, right? So we use minus. So do be careful when you write down the models from the output from your software. Okay, so we use TS Arima, right, to in the TS forecast package, right? Here, you need to specify the order, right? And the order will be a three-component vector, right? The first one will be the AR order, and the difference order, and the MA order. Okay, so this TS Arima function. And then you look at the output. You will check whether the the coefficient of the different terms, the p-value, whether they are significant or not. And you also need to look at the AIC, BIC information criteria, right? Because if you have maybe different models to fit your data, right? So you need to check which model is the most appropriate one and look at the AIC, BIC information criteria. This evaluate the fitting model is very important. So you need to understand, right, what you need to do in order to evaluate the model. First, the p-value of the terms of in your model. For example, the MA term or AR term, right? And the p-value should be smaller than the significant level you determined, right? Otherwise, that maybe terms might not be significant in your model, right? You need to consider another model. And so after you fit the model to your stationary time series, you need to check, right? You need to check the residuals. If the residuals follows so-called white noise process, means the residuals follows normal distribution with zero mean and constant variance and no correlations, right? IID normal distribution. Then your model actually captures almost all the information from your time series, right? So the residuals are the white noise will be the criteria, right, to indicate whether you have extracted all information from your time series. So this is why we say it's very critical. You will look at the residuals of your model, and you first you after for the ACF after leg 0, right? Because leg 0 the ACF always equal to 1, right? All ACFs with maybe certain legs, maybe up to a certain number, certain legs, and they are within 2 standard deviation. And all the PSAFs are within 2 standard deviation for many legs. That means there are no correlations among your residuals, right? And you can check the normality of your residuals using QQ plot or this Shapiro-Wilk test, right? And you can check the independence of the residuals using the Elgin box test, right? You look at the test of your residuals, right? Of your residuals, and check whether the mean is 0, and check whether they follow normal distribution, and check whether, of course, the white noise itself should be stationary, right? And then Elgin box, because this stationary means constant mean and variance, right? And then the residuals are also independently distributed, right? So this you need to check the residuals. And then you can also plot the residuals from your model, right? Then you should see no so-called clear patterns, right? That should be distributed along the timeline with no obvious patterns. Okay. Of course, you can evaluate your model, right? You look at the AIC corrected and BIC information criteria, and sometimes, yeah, you can also report the error measures, right? To and to see whether your model fits your data. Okay, then we use MA model. We can do a forecasting, right? We do forecasting, and this is a MA1 model, and so we need to rely on the white noise, right, in your forecast, especially in the past period to do your forecasting, and in all future period, and the white noise has not been realized, and we don't know, so you need to use the forecasted value to do the forecast, right? So this is a typical, for example, this the one-step forecast using the MA1 model. And uh, unfortunately, MMQ model has so-called maybe short memory, right? For any forecasting steps beyond the order of your model, and the forecast will be the mean of your time series, right? So this is maybe the short memory property of the MA model. Okay. And of course, we will the forecasting will also give you a confidence interval, right? And the output from R will generate the confidence interval of your forecast. Okay. And then yeah, this is a summary for MA model, right? So MA model basically we predict the values of time series by removing past white noise from the data, right? Basically, you need to rely on the past white noise in past period. And white noise are IID distributed residuals, right? And from follows normal distribution with mean zero and constant variance. And so MM model can be stationary in terms of mean and variance. Okay, MM model is always stationary, but for MM model, we care about the invertibility, right, of MM model. Whether MM model can be represented by infinity AR process. Okay, this is called invertibility. So we didn't mention this in the slides, but in the materials, in the record video, right? You should watch the video to understand the invertibility of ML models. Okay. So for ML models, MAQ process, the ACF have a cutoff after like a Q, right? But PSF decays exponentially, right, with increasing lag, right? No clear cutoff for PACF, right? Okay. Yeah, AR model. Okay, AR model basically uh we you can also use the ACF and PSF to identify whether an ARP process is appropriate to model your time series, right? So if you look at your ACF of your time series, if the ACF decreases exponentially, and or shows a damped sinusoid pattern, but the PSF have clear cutoff, right? You can consider the ARP process to model your data. Okay. And here the ARP process, this is the model, right? Here, remember, this is a constant, not like the MM model. In the MM model, that constant is also the mean, right? But for AR model, this constant is not the mean. So this is why you must be careful when you look at the output from your from R. Okay, you can see that they are different. Okay, and for AR process, we care about the stationarity of the process. So basically, for AR1 process, so the absolute value of that parameter phi1 is less than 1, then the AR1 process is stationary. Otherwise, it's not stationary. Not stationary means you have you do not have a constant mean or variance, right? And the autocorrelation for AR1 process, You can see decays exponentially, right? And PSF will have a clear cutoff. Okay. And here you can see, you look at this AR1 process, because remember in AR model, we use plus, okay, plus phi1 minus yt minus 1 phi2 minus t times yt minus 2, okay? So here different from the MA process. In MA process, remember the coefficient we use negative, okay, negative or minus theta 1 something, okay? So you must be careful when you write down the formula, write down your model, right, from the output. Okay, here you can see, when you fit the AR process, here, this is the constant you should put in your model, okay? And however, the mean refers to this intercept, right? Okay, so they are different, right? So when you fit, you write down your model, right, from the output. You must be careful for the AR process. Okay, so this is forecasting with AR1, where AR model. Basically, AR model, you have the forecast. For example, even one period ahead forecast will depend the past values. And for the H period ahead forecast, here you can see this will depend the value in your time t value. And then will decreases exponentially, because phi1, the absolute value of phi1 is less than 1, right? Eventually, you can see with t or h goes to infinity, and then the forecast will be almost the mean of your time series. Okay. This is you can use this is the summary, and AR model predicts the value of time series by adding up the effect of all the past observations, right? And so we can use ACF and PSAF to identify the AR model, right? If the PSAF has a clear cutoff after P lags, then while ACF decays exponentially, right? You can consider AR process. And this is what we discussed, okay, in seminar 4, okay. Okay, so let's go to seminar 5. Okay. Okay, so today we will discuss the non-stationary time series using ARMA and ARIMA models. Okay, so here in seminar 4 we discuss the AR model and MF model separately. Now, let's first start with this activity, right? So this AR ARMA series, and we import the ARMA series, this time series into R, and then we look at its ACF, it's a line chart, ACF, PSF, right? And then you discuss what you can discover from those graphs, okay? Okay, maybe I give you, let me see, 3 minutes, okay, 3 minutes to import the data, okay, into R, and also generate the ACF, PSF line plot, line charts, and see what patterns we can observe. Yeah, try to import the data into R and then use either TS explore function, uh, or you use TS ACF, TS PACF to generate the ACF and PACF of the time series. All right, so let's do it together. Then you can share your observations. Okay, so let's import the data and then to generate the ACF and PSF and also maybe some line charts of the original time series. So let's use this uh, package, TS forecast package. Okay, so let's say a ARMA1. Let's import the data. Okay. Let's see what the data. Okay, the data have two columns. The first column is date. The second column is series. We need to convert the date into the date format. Right? Currently, it is character format. And also, we convert the series into time series object in R. So I believe everyone should be able to, right? Uh, to the transformation. Okay. Okay. Okay, so we convert the first column into date format and also convert the series into a time series object in R. And then now let's look at the ACF and PSF of this time series. Let's specify the lag equal to 24. Okay. Okay, so this the ACF and the PACF of this time series, right? And you look at the ACF plot, and you look at the PACF plot, and can you share your observations? You can share your observation in the chat box. Okay, chat box. so that I can see whether you are still in front of your laptop or not, or computers or not. Do you have the same output from R for this time series? Okay, yeah. So can you share, Elma, can you share, yeah, and we Kong, Alfred, can you share your observations? Maybe a simple words, a few words, okay, in the chat box. For example, you look at the ACF and the PSCF. Okay, Alfred, I believe you say maybe the ACF would decay exponentially, or maybe boost decrease decay exponentially, right? Okay, but you can see, but if you look at ACF and for the lag from 15 onwards, and although it is look within 2 standard deviation, right? But you can see it becomes bigger, right? With time lag, right? Increasing lags, okay. And if you look at the PSCF, uh, you can see they still have non-zero values, even if you have lag up to 20 or even 23, right? 24, right? Okay. So here, if you consider the ACF or PSF, whether they have a clear cutoff to select whether AR model or MA model is maybe challenging, right? So it's not clear whether you should consider AR process or MA process for this time series, right? Because both ACF and PACF that decrease, yes, that decrease or that decay exponentially in terms of the lag. This is typical, we say, characteristics of short term, right? Short term correlation for time series, and if they are stationary, right? Of course, you can use TS Explore, right? TS Explore to see, let's see, maybe some test, okay? Yeah, so this is a line plot of your original time series. And okay, this is a distribution of the data. And I mean, they are not normally distributed, right? Because they are not if you look at this curve and the fitted probability curve, and they are not seems normally distributed. And if you look at the QQ plot, and especially in some data points, they are not along this 45-degree line. And yeah, ACF, and of course this is with time lag 8, okay. Yeah, so and let's look at the test, right? If you look at the test, location test, you reject the null hypothesis, means the mean is not 0, right? And Shapiro-Wilk test, and uh, so you will not reject, right? You will not, because that seems normally distributed, okay? This ADF test, right? ADF test, the p-value. Remember, we discussed in seminar 4, ADF test is one of the tests to test whether there is a unit root, right? So the null hypothesis is there is a unit root. And so you reject, if there is a unit root in your time series, means your time series is not stationary, right? Is non-stationary. And now you reject that, means it is stationary, right? And the Aljun box test, right? Independent. Here we reject the independent assumption. So the time series, the data are not independently. They have correlations, right? They have correlations. Okay. Yeah. So this is you look at the ACF and the PSAF, so it is not easy for us to determine whether AR process or MA process is so-called appropriate for to model this time series, right? So this is why we come up with this AMA process. Okay. Yeah. Okay. So this is what we can observe. Okay. So here you can see there are no clear cutoffs, right? For that there are no cutoff in terms of ACF or PSF, but it decays exponentially, right? Because we say if it does not decay exponentially means there could be trend in your time series. Then your time series is non-stationary, right? So we hope the ACF, PSF decays exponentially in terms of with respect to the lag. Okay. And the PSF does not show clear cutoff either, right? It is more like the MIQ process decays exponentially, right? So for if you have a stationary time series and the ACF and PSF does not have a clear cutoff, but they decay exponentially, right? So it means you have a stationary time series, but you may not be able to fit with purely AR or MA process. Okay, so we will consider the AMA process. Okay, so this is the AMA process, the model. You can see YT equal to this constant plus the AR process, and this is MAQ process. So this is an integration of both AR process and MA process, ARP process plus MAQ process. Okay. So you can see there are many parameters you need to estimate, right? Here there are P parameters in terms of the AR process, and there are Q parameters in terms of the MA process in your AMA model. And you also need to estimate the mean. You also this constant is not mean, okay? It's a constant in the model, and you also need to estimate the variance of your white noise, okay? So you can see there are P plus Q plus 2 parameters you need to estimate. Okay. So this epsilon t is the white noise. Okay. So after you fit the AMA PQ model and you check your residual and whether the residuals are white noise. Okay. Yeah. So this ARP process and MAQ process are special special examples of this MRPQ process, right? One of the parameters is 0. Okay. So this is a AMA11 process. Okay, AMA11 process. And so this is the model, right? And then if you calculate the mean and variance of this process, so this is the mean equals this constant divided by 1 plus 1 minus phi 1, right? And the variance, okay, the variance is a little complex to calculate, right? You need to write down, for example, yt minus 1, and then also y, because yt minus 1 also depends on epsilon t minus 1 something, then the variance you can see depends on both epsilon t minus 1, okay? And then this is the variance of the AMA11 process. Okay, and the AMA PQ process is stationary if the embedded ARP process is stationary. For this AMA11 process, so it is stationary only if the absolute value of these parameters, the AR coefficient, AR coefficient is within 1. Okay, and it is invertible, right? It also depends on this, right? Theta 1. So theta 1 should be also within 1, okay? The absolute value. And then the autocorrelation, you can see if you calculate the autocorrelation of AMA11 process. So it is the simplest AMA PQ process, right? 11. AMA 11. So you can see the ACF decays exponentially because this part is a constant, right? Phi 1, theta 1 is a constant, and this when K increases, so your ACF decays exponentially, right? So this is why when you observe the ACF plot or PSF plot, it decays exponentially, but no clear cutoff, right? Okay, so with ACF, PSF show exponential decay simultaneously for MRPQ process. And yeah, if you observe exponential decay of your ACF and PSF from your original time series, then you may consider it is a MRPQ process. Okay, use MRPQ model to fit your data, your stationary time series data. But sometimes to determine the orders, right, in your RMRPQ model, P and Q, and sometimes it's not easy, right? I mentioned in seminar one, sometimes it's art, right? So you need to see so which P or Q is the most appropriate MRPQ model, right, for your time series. And sometimes you need to use a try and error method. You try with different P and Q values, and until and you of course you can look at the model evaluation various criteria, the AIC, BIC information criteria, and to find maybe to determine the best most appropriate model. And but you also need to look at the residuals, right, for each model, and whether the residuals are white noise, right? So usually you can start with, for example, P equal to 1, Q equal to 1, right, to try and then see the information criteria, the error measures of your models, and see whether those components are significant, right? And then check the residuals, okay? And then you can increase the order progressively, right? Progressively, right? From maybe P equal to 2, Q equal to 1, and test and compare different models. So this process stops when the coefficient becomes insignificant or the goodness of fit. For example, this information criteria declines compared to lower order models. Remember, so if you can find, because the more parameters you need to estimate, sometimes you will be difficult, right, to get a more accurate estimate, right? So you can see if you can find maybe the lower values of P and Q satisfy your requirement, for example, in terms of the coefficient significance, in terms of the goodness of fit, AIC, BIC information, then you may stop, okay? Okay, so let's look at activity 5.2, okay? Look at this AMA11 process and identify the parameters mu, the mean of this time series, phi 1 and theta 1, right? Assess the stationarity of the process. Okay, I give you 2 minutes to do the calculation, especially for the mean. Okay, and then you can share your answers in the chat box. Okay. It should be quite straightforward, right? You look at the AMA11 process, the model, and just apply the formula, or you can derive the mean by yourself, right? And you can also look at uh, what is the value of phi 1, what is the value of theta 1, okay, in the process. If you have the answer, please share your answer in the chat box. Okay. Anyone wants to share your answer? Should be not difficult, right? Okay, so any answers? Can you share? Can you share what is the mean? What is phi 1 and theta 1? Just give me. Okay, great. We have uh Alfred, we have Jamin. Okay. We have different answer, right? You can see, you look at the answers from both of them. We have different answer. Okay, we have Grace. Okay, Grace has theta 1, phi 1, theta 1. Okay. Okay, so I can understand. Okay, Yuan Eng, Xin Yu, you have okay, seems we have okay, you both of you have the same answer. Okay, any more answers? Yeah, Han Xu, you got a Ming. Okay, great. Wiki, yeah, you have Ming, you have Phi 1, Theta 1. Okay, great. Okay. Okay, remember our model. Okay, YT, right? This is AMA 11 process, right? YT equals uh, delta plus phi 1 YT minus 1, right? And remember, we say, yeah, this is epsilon t, but we use minus, right? Theta 1 epsilon t minus 1, okay? Yeah, so now let's look at this. So I believe you should be able to find that phi 1 should be this negative 0.6, right? And then theta 1 should be negative 0.3, right? Because remember, we use plus phi 1 times yt minus 1, while here is minus theta 1 times epsilon t minus 1, right? So you must be careful, okay? Here, phi 1 equals negative 0.6, and theta 1 equals to negative 0.3, okay? Now let's look at the mean. If you take the expectation, right? You take the expectation from both sides, right? This you also take expectation from both sides. You will see this will be delta plus, because it is a stationary time series yt, right? So they have the same mean, means yt, the mean of yt and the mean of yt minus 1, they are the same thing, right? Equals phi 1 times, we use mu. Let's say we use mu, right? So mu equals delta plus phi 1 times mu. And then mu will be delta divided by 1 minus phi 1. Okay? Yeah. So this will be 3.9 divided by 1 point negative 0.6, which is the 1.6. Yes, mean will be 2.4375. Okay, we keep 4 decimal places, right? Yeah, this is the mean. Okay. Yeah, do be careful. Okay. And when this is you must be careful when you calculate the different parameters of your model. Okay. So stationarity of the process, we say, will depend on this phi, right? And now phi, the absolute value of phi equal to 0.6. So it is stationary. Okay, so this process will be stationary. Okay, so the stationarity of the AR process, AMA process, will be determined by the AR terms, while the invertibility of the AR process, AMA process will be determined by the MA process. Okay, so as long as the absolute value of this parameter is within unit the circle, right, or less than 1, so it is stationary. Okay. All right, so this is just to give you a reminder. You must be careful. Okay, you must be careful when you calculate your model parameters. Okay. All right, so to fit the AMA model, we can still use the TS-ARIMA function. Okay, TS-ARIMA function, and then you can just specify the order, right? So this is the AMA 11 process. Applied on this time series. Okay, so I will not demonstrate these steps because you have the code. Okay, so I will just focus on the activities. Okay, so this is a constant estimate. Basically, the constant estimate will be in your model. Okay, that delta, right? Delta. And this, remember, plus phi 1 times this AR term. Okay, now this AR1 term is 0.8475. Okay, and then we have plus epsilon t minus theta 1 times epsilon t minus 1. So now the AR term, this theta 1 equals 0.5420. So you should minus 0.5420 times epsilon t minus 1. And this is a random or this white noise in period t, right? So this is the model. Okay, this is the model. And now you look at this output. You look at the p-value of each term. You can see the AR term is significant, means this is significant, this term. And then the MA term is also significant because the p-value is almost 0, right? So the MA term, 0.5420 epsilon t minus 1 is also significant. And the intercept or the constant, right? Intercept is not constant. Okay, this is actually your mean. Okay, this is the mean. Remember, this is the mean. Okay, and this is constant, right? Constant. The mean is also significant. Means your model should should contains this constant term in your model. Okay, so you can see this is the output from R, and you should be able to write down the model, right, based on the output. And you should also be clear about the mean. The mean of the time series, which is 4.8863, right? This is the mean. Okay, this is the mean. And then the AIC, BIC, you look at the AIC and BIC, and suppose you want to maybe use other models to fit this time series. For example, you might consider maybe AR2 process or MA2 process, right? Or AR3, MS3, or even AMA2-1 process, AMA1-2 process, right? You want to compare each model, and then which model maybe the best, right? You can look at the AIC, BIC, besides look at the significance of the terms in your model. Okay, you can look at the AIC, BIC criteria, and then determine and the best model for your data. Okay, and always remember the simpler the better, right? You have a simple model with maybe lower values of P and Q, and the better, right? Because you don't need to estimate more parameters, so you can have maybe more accurate estimation. Okay. All right, so this is output from R, right? So you must be careful, okay? You must be careful. And when you fit, eventually you determine the orders of your AMA model. And then you also need to evaluate the model, right? Evaluate the model, you look at the residuals, right? Residuals, whether the residuals follows white noise process, right? You look at if the residuals are white noise, means your model extract almost all information, right? All information from your time series, right? So your model so is useful. Okay. All right, so let's look at the activity, right? Let's import this data in R and check its line chart, ACF, PSF, and then discuss the column series is AMA process or not. Okay, and if yes, so which orders you want to try, you want to suggest, and then we can feed this feed an AMA model for this time series, and then evaluate the chosen model. Okay, I give you 5 minutes to do this. Okay, I give you 5 minutes to do this because the activity, the code actually is very. If you can do the activity, so you should be able to perform similar, demonstration in the slides. Okay. So I give you maybe 5 minutes, then I will demonstrate the steps. You can try different AMA models, right, with different PQ values, and then eventually you select the most appropriate AMA model to fit this time series. So first, you need to ensure that this time series is stationary, right? This time series is stationary, and this time series is not white noise process, right? If you have a white noise process, you don't need to do anything. Your analysis will stop, right? Because you cannot extract further information from a white noise process, right? So first, check whether the time series is stationary and whether the time series is a white noise process or not. You actually can copy the code used for the slides and then just change the code, right, a little bit, and just may change the AMA series 1 to AMA series 2 and import the data, and then change the date format and convert this into a time series object, and then look at the ACF, PSF, and then fit with different AMA model, right? AMA model, and then compare with maybe different models and select the most appropriate models. Okay. Yeah, you can always try with lower orders AMA model. Okay, PQ equal to 1, PQ equals to 2, right? And then let's see. And for any higher orders AMA PQ model, actually it's not usually, right, the lower order AMA PQ model will be sufficient to fit the data. All right, so let's do it together. Let's do it together to import data. Let's import the data into R. Let's look at this ARMA series. Okay, similar, right? The first column, two column, date and series. And then we need to change the format of the first column and convert it to a time series object. So remember, it is a monthly data, okay, monthly data. Later, we may also use this data. So because it is monthly data, if there is a seasonality, so we will assume the seasonal cycle will be equal to 12, okay? So we convert it to a time series object, okay? Let's check the data again. Okay, so now the data has been converted to a time series object. And then let's look at ACF, PSF. Okay. Maybe we specify lag equal to 24. Okay, so this is the ACF for 24 lags. And uh, yeah, look at the ACF and then PSF with lag 24 lags. Okay, we can observe a similar pattern, right, for series 1, right, AMA, the previous data set. You can see the ACF uh, decay quite faster, right, because it's a stationary time series, right, and in the previous a few lags. And however, you can see there are no clear cutoff after certain lag. For example, in this ACF, there are no clear cutoff after lag 1, because for the ACF for lag 3 and lag 4, it is beyond 2 standard deviation, right? And if you look at the PSF, right, similarly, it is there is no clear cutoff after, for example, leg 4, right? Leg 4, because if you look at the PSF, there are still quite big values, right? Different from 0, although it is maybe within the 2 standard deviation, but it's not significant from not 0, right? They are still quite big values, okay? And so, of course, for this, if you look at the PSF, right? If you look at the PSF, if you want to say that after leg 4, there are cut off, that's fine. You can try with AR4 model, right? You can try with AR4 model, okay? And if you look at the ACF, right? If you look at SEF, you say if you want to say that after leg 4, there are cut off. Okay, you can try with MF4 model, right? MF4 and AR4, right? This both model you can try. Okay, you can try, and then you can also try with AMA model, right? AMA starting with low orders, and then you compare, right? You compare which model is better. Okay. Yeah. Do you have the same output in terms of the ACF and the PSAF? Of course, you can use TS Explore, right, uh, uh, to explore the original time series. Okay. If you look at the line plot, and you don't observe trend or something, maybe, right? So maybe it is a stationary, right? Okay, and you look at the distribution, right? That seems not quite normal, but we will see. Okay, the QQ plot, and yeah, SAF, BSF we already have, and you look at the test, right? You look at the test. So clearly the mean is not zero, right? Because your original time series, the mean is not zero. And it seems normally distributed, right? So the p-value is bigger than the significant level, usually 0.05. So you will not reject this normality assumption. And this ADF test, right, p-value is less than 0.05, means it is stationary, right? This your original time series is stationary. So you can use AMA, ARMA, AMA models, right, to model your time series. And you look at the L box test, and you reject the independent assumption. So clearly your original time series is not white noise, but it is stationary, right? It's not white noise, it is stationary. So you can apply the AMA model, right, to model your data. Okay. All right. Yeah. So now let's look at the different models. Okay. So we observe the ACF, PSAF, and we know the time series is stationary and it's not white noise, right? So we want to use AMA model to extract maybe information from the time series. Okay. So we can compare different orders of AMA model, right? And then select maybe the best one. Okay, let's use a summary to function to select to compare. Okay, to compare various AMA models. Okay. So let's if you start you want to start with maybe AR4 process. Okay. And you also want to try with MA4 process, right? Because you look at the ACF and PSF, you want to try with these two process. Okay. And you also want to try with lower order AMA process. Okay. Maybe we try with the AMA 11 process. Okay. And then yeah, you want to try with maybe other orders of AMA process. For example, AMA 21 process. Okay. And maybe AMA 12 process. Okay. 12 process on the okay, or AMA 22 process. Okay. So you try with different models and then compare among different models. Eventually, you select maybe the best model. Okay. Okay, so we try with this 6 different models. Okay, starting with the simple AR4 process. Okay, if you look at the AR4 process, all the you can see AR terms are significant, right? And also this constant term is also significant. Okay, and but you look at the AIC information and BIC information, okay, 720, 738, okay, and then you look at maybe the MA4 process. MA4 process, you find that maybe MA3 and MA4, these 2 terms are not significant, okay, not significant. And you look at the AIC, BIC, and it is bigger than AR4 process. So you can kill this model, right? Compare between these 2 models, AR4 is better, right, than MF4, okay? And then you look at the ARMA 11 process, okay? All the terms are significant, and the AIC, BIC, you compare with AR4 model, AR4 model, it seems you can see it is the AIC becomes larger, right? So maybe AR4 is better than this ARMA 11 process, right? In terms of the AIC, BIC, right? They are smaller for AR4 process. And you look at it, ARMA 21 process, AIC and all terms are significant, but this MA1 process, you can see the p-value is bigger than 0.05. Usually we use 0.05, the significant level, right? But not quite big, right? And it is less than 0.1. So, but it is, you can say, maybe within, if your significant level is 0.1, it is significant, right? If your significant level is 0.05, you will say it's not significant, okay? And then you look at the ARMA 1-2 process, ARMA 1-2 process, and the AR terms is not significant. 2 MA terms are significant. And you look at the AIC, BIC, and compare with ARMA 11, it is becomes worse, right? AIC, BIC becomes bigger. Okay, so the ARMA 12 is dominated by ARMA 11, right? ARMA 11 is better. Okay, now look at ARMA 22. If you look at ARMA 22, 2 AR terms are significant, and MA2 term is significant, but MA1 term is not significant. Okay, and then you look at the AIC, BIC, right? AIC 722 is better, right? Better than ARMA 21. Okay, smaller than ARMA 21. And you compare with AR4 process. Okay, almost, comparable, comparable, right? And look at the BIC, 738, and this 739, almost, right? Almost very close. Because you can see this also have uh, 4 terms plus 4 terms in your model, and AR4 also have 4 terms, right? In your AR model, right? So the AIC, BRC are quite nearer, right? Near to each other. Okay. So anyway, for this time series, and this among these six model, uh, you may consider this AR4 process, right, to feed this data, or you may consider this ARMA 22 process to feed the data. Okay, because you can see the information criteria, the values are very close, and also significant in terms of AR terms and some the values. right? Of course, what I just mentioned earlier, you also need to uh, check the residuals, right? If the residuals from, for example, AR4 model is a white noise process, that means your AR4 process is perfect. If the residuals of ARMA22 process also satisfy the white noise assumption, right? Also, white noise means ARMA22 process is also appropriate, right, to model this time series. Okay. Do you have any questions? Do you have any questions regarding model comparison, and also eventually you select the so-called the maybe most appropriate model for your data? Okay, you have no questions. That's good. So I assume you follow what I said. Okay. All right, I hope you're all clear with this process. So actually, model selection is not easy, right? So you might have, I mentioned in seminar one, right? Statistics is not like mathematics, right? Statistics sometimes you need your own judgment. You need to maybe you have some criteria to satisfy. As long as maybe the model fits or meet your requirements, then you can say that model is good, right? So statistics are not, like mathematics. You have a rigorous process to select whether your answer is correct or wrong, right? So for this activity, basically you can consider AR4 process and then check the residual, okay? And then you can consider the ARMA22 process and then check the residual, okay? Now let's assume, okay, because now we are looking at the ARMA process, okay? ARMA PQ process. Let's assume we select ARMA22, okay? We select ARMA22 model for this time series. Okay. Now we now look at the residuals. Okay. So first we select ARMA22 as the model. Okay. ARMA22. Let's make this model. Okay. Let's look at the model again. Okay. Let's look at the model again, and also we check the residual. Okay, maybe we check the residual. So let's check the residuals of this ARMA22 model. Okay, if the residuals are white noise, that means this ARMA22 model is appropriate, right? Okay, so let's look at the, this is we have for the ARMA22 model. And then you look at the test. Maybe let's go to the test. Test on the residuals. Okay, test on the residuals. Okay, so here you can see the location test, right? T-test mu equal to 0. So we accept the null hypothesis, means the residuals, the mean is 0, right? The mean of the residuals is 0. And this Shapiro-Wilk test, normality test, so means the residuals follows normal distribution. So we accept this hypothesis because p-value is bigger than 0.05. Okay. And independent test, and so we accept the null hypothesis, right? So we say the residuals are independent, okay? And then, of course, the stationary, because so they are white noise, and white noise are stationary, right? So this p-value is less than 0.05, okay? So we can say this ARMA22 process uh, fits this data very good, right? Perfectly, okay? And you also look at the ACF of the residual. You can see, yeah, ACF like 0 is always 1, right? Always 1, but all the other ACFs with lag bigger than 1, bigger than 0, right, from 1 onwards. And the ACF, you can see they are within 2 standard deviation. So they are considered as 0. So no correlations, right? And then this PSF, right? All PSF are within 2 standard deviation. That means, yeah, no correlation. So for the residuals, so the residuals are independently distributed, right? This is consistent with the test, right? Consistent with the test, okay? All right, so you can see for this time series, we say ARMA22 process is appropriate, right, to model this time series. But of course, you can check with AR4 process, right? Because we just compare the AR4 process is also maybe appropriate, right? So let's do a additional test, okay? Maybe we model a AR process, okay, AR4 process. So let's look at the, maybe you consider using AR4 process to model this time series. Yeah, so we directly go to the residuals, okay, residuals. And you look at the test, the ACF also looks good, right? So all ACF with lags from 1 onwards, ACFs are considered to be 0. And PACF, right? Also, you can see, look at this PACF. So all PACFs are within 2 standard deviation that can be considered 0. And if you look at the test, right? So the residuals have mean 0, and the residuals are normally distributed, and the residuals are independent, right? And of course, they are stationary, right? So this white noise process. So the residuals from AR4 process is also a white noise process. Okay, so we can say AR4 model can also fit this data, right, to model this data. Okay. Are you all clear? Okay, Alma, you say, if there are more than one appropriate model, what criteria should we prioritize for selection? I mentioned, right, you can consider AIC, BIC, and sometimes, right, the less parameters, the better, right? The less parameters, so you have fewer parameters of your model, the better. And also, you consider the purpose of your study, right? Sometimes you can see, I just want to use the autoregressive model, right? Because it's easy to interpret. Then you can use AR4 process for this example, right? And because actually for AR4 process, you can see the AIC, BIC are smaller. AIC, BIC values are smaller. And also they have the same parameters, right? AR4 process, you have 4 parameters. And AMA2 process, you also have 4 parameters, right? So now you can see whether you want to use AR4 or AMA2. So there are no so-called the definite correct or wrong answer for this, because both models meet the criteria because the residuals are white noise, right? So both models extract the information from your original time series. So both models are appropriate. Then you will determine based on your, for example, the purpose of your study and whether it is easy to interpret and maybe other criteria or considerations you may have. Okay. Okay, great. Yeah. So yeah, so for this time series, anyway, we have at least 2 models which we can use, right, to capture the information, extract the information from the original time series. All right, so let's go back to the slides. Okay, slides. Okay, so the forecasting. Okay, the forecasting with the AMA PQ model. Okay, so let's look at the simplest one, the AMA 11 model. And this is, for example, you want to do one step forecast, right? You want to forecast T plus 1. So this, you apply the model, and this actually refers to so you will have delta plus phi 1 yt. You actually have 2 terms, right? Epsilon t and theta 1 epsilon t minus 1. Epsilon t plus 1. Sorry, this should be epsilon t plus 1 and minus epsilon theta 1 times epsilon t. Okay. But because you are doing forecast, this guy has not appeared. So we will not include this guy, epsilon t plus 1, right, in your forecast for t plus 1 period. Okay. So this is, and then epsilon t will be yt minus yt hat, right? This your forecast, your actual value. So they are the realized white noise in time t, okay, in time period t. So you can see the forecast value depends on the most recent series value, here yt, and the white noise, right? Yt t period in period t, right? This white noise in period t. And if you do 2 step forecast, okay, 2 step forecast for this AMA 11 model, right? So yt plus 2 hat, and then you substitute your AMA 11 model, and this will be phi 1 yt plus 1 hat, because yt plus 1 you need to use the forecasted value, right? So you substitute the forecasted value, and then plus epsilon t plus 2, and we will not include the epsilon t plus 2, and then minus theta 1 times epsilon t plus 1. And epsilon t plus 1, because you don't observe yt plus 1. So you also substitute yt plus 1 with your estimate, with your forecasted value. So they will be cancelled out. Then this will be your forecast 2-step forecast, right? So equal to delta plus phi 1 yt plus 1 hat, right? And then because this you substitute to here, so you will have yt plus 2 period forecast depends on yt, right? Depends on yt. And then so on and so forth. This will be, for example, h step forecast, yt plus h. Then you will have this formula, recursive, right? This delta plus phi 1 times yt plus h minus 1 hat, right? This also forecasted value for any h big than 2. Okay, and then so you can see eventually all this will depend on yt. will depend on YT, right? For any uh, edge step ahead forecast, and then this will be back to YT, okay? And so you can see for any step ahead, which, for example, this edge is bigger than 1, edge from 2 onwards. So this MA term will not play a role. Only the AR term, right? Only the AR term will play a role in your forecast, right? You can see, because this is the typical MA model, the property, the short memory, right? Remember for MA1 model, in seminar 4, we just covered, right? We just do a quick review. MA1 model, for any forecast, the period is bigger than 1, then it will be the series mean, right? So the MA term will disappear in your forecast, and only the AR term will play a role in your forecast. Okay, for any forecast steps bigger than the AMA, the Q, right? The Q order in your AMA PQ model. Okay, only AR term play a role. Okay. So this is the forecasting. Okay, forecasting with the AMA 11 model. And of course, you will also generate the confidence interval, right? Confidence interval of your AMA, the forecast. Okay, so you can use the TS forecast function, right? So we have used this many times, right? Okay, yeah. So let's do activity 5.4. So calculate the 12 months forecast series. Remember, it is monthly data, okay? And the AMA series 2 is monthly data, and you calculate 12 months ahead forecast, and then generate the forecast value and the predicting intervals, okay? Yeah, I think it's quite straightforward, right? So I give you 1 minute to do the steps. Okay, suppose we use the AMA 22 model, okay, AMA 22 model. Then we use, based on the AMA 22 model, we do the forecast. It's quite straightforward, right? So I just demonstrate. Remember the AMA 22 model, we fitted AMA AMA 2 AMA, okay? This is the model, the object name. So you just use a TS forecast function, okay? AMA 2 AMA model, and you forecast the 12 period, and let's plot the data, plot the forecasted data, okay? So it's this you will have. You can see this is the confidence interval, right, of for each period forecast, and this will be the plot of your forecasted value. All right, so it's quite straightforward. Once you fit the model, once you have the model, and then you just use this TS forecast function, right, to do the forecast. Okay. Okay, so let's continue. Okay, let's continue. So now let's discuss your observations of the forecasted value generated by AR, MA, and AMA models. Actually, I provided some hint, right, for AMA 11 model, right? So okay, can you share your observations in terms of the forecasted value generated by AR model, MA model, and AMA model? Yeah, you just maybe a few words to describe. For example, the forecast value generated by MA model. Maybe after Q period, all the forecast value will be the series mean, right? And for AR model, right? Look back the AR1 process, right? The forecast value will depend on maybe YT and then approaching the series mean, right? Because with your forecast period increases to infinity, then your forecast value will be your series mean. Okay, can you share? Yeah, can you just strengthen your memory, strengthen your your understanding of the forecasted values by AR, MA, and ARMA models. You just share a few keywords, okay? So so that I know you are still with me and also participating in this seminar, okay? Any keywords, any observation, or you can have your own observation, right? For based on the forecasted values by these three models. So what about the ARMA model, the forecasted value by ARMA model? All right, maybe you are all tired, right? So yeah. Anyway, for AR model, you can see it will depend on the past values, right? The forecast value will depend on the past series values, and with the forecast period increasing, and the forecast value will be approaching the series mean, right? And for MA model, right, MIQ model, after Q period, all the forecast value will be the series mean, right? And for ARMA model, right, it is incorporate the characteristics of both AR and MA model, right? And then the forecast value will gradually depend on the past value, and also gradually approaching the series mean. And for any forecast period which is bigger than Q period, so the forecast value will be independent of the MA terms in your ARMA model, right? So this is what we can observe. All right, it's a quick summary. Okay, quick summary. The ARMA PQ process is a combination of these two processes, and both ACF and PACF decay exponentially, right? But have sometimes you may observe both cut off after like a P or like a Q, right? So this is why I say sometimes you can consider AR model or ML model, right, to fit your data. And this stationarity of MRPQ model depends on the stationarity of ARP part. And the invertibility will depend on MIQ part, all right? And the mean is depends on the ARP part, okay? Of course, it's not easy to get the variance of an SAF calculations for MRPQ model. It's very complex, okay? And yeah, you can see the forecasting step H. If the forecasting step H exceeds the MI order Q, then the forecast value is purely a result of the prediction based on the ARP process, right? ARP part. Okay, it means the MAQ part will not play a role in your forecast. Okay, but if it is smaller than MAQ process, the past white noise will play a role in your forecast value, right? Okay, so this is what we can observe. Now, yeah, let's have 5 minutes break. Okay, let's have 1 minute break. And then we will discuss the ARIMA process, okay, for non-stationary time series, okay. So let's come back at 8:45, okay. So please come back at 8:45. All right, everyone, we are back. Let's continue, okay? For this ARIMA model, so basically, if you understand the ARMA model, you should be able to understand the ARIMA model. So I will not go through each page, okay? So because ARIMA model deals with non-stationary time series, right? Especially there is a trend, and then you use differencing to remove the trend and then get a stationary time series. Okay, the differencing time series. Okay, so this we use ARIMA PDQ model. Basically, you do D step, D order difference, and then that time series will be stationary. Then you fit this stationary difference in time series with AMA model, right? AMA PQ model. So this is the ARIMA PDQ model, right? And some typical, for example, this if you have after you get a difference, and then you have this purely white noise, which actually indicates your original time series is a random walk process, right? Random walk process means yt equals to yt minus 1 plus epsilon t, right? So this is called a random walk process. And if you have a constant in your model, so this is a random walk process with drift, right? Okay. So the random walk process actually is the ARIMA 010 model, right? And because there are no PQ terms, no AR terms, no MA terms, right? To remember, we are focusing on the difference in time series now, right? After do D order difference, right? Difference order D, you have a stationary time series. Now you can use AMA model to model this difference time series, okay? Yeah, this MA model actually is if a time series become MA model after differencing, for example, after first order differencing. So this is the ARIMA 011 model. So basically, the differencing after one order differencing, it is MA1 process. Okay, so this is if you write it in this is the differencing time series equals to the mean plus epsilon t minus theta 1 epsilon t minus 1. Okay, so this is ARIMA 011. Or after first order differencing, you have AR1 process. So this will be ARIMA 110 model, right? So this is ARIMA 110 model. Do remember, we are working on this differencing time series. So after first order differencing, we focus on this series, okay, this time series. Okay, so we can consider ACF, BSF, right? If you look at your original, right, original time series, if you look at the ACF, the ACF decreases very slowly, not exponentially, right? Not exponentially, but only decrease very slowly means there are clear trend in your time series, right? Then because your time series have a trend means your time series is not stationary, and then you do differences. So after maybe some order of difference, you have this ACF and PSAF. You can see that decrease exponentially of this differencing time series, right? After difference, and that decrease exponentially. That means it is could be stationary, right? The time series after differencing could be stationary. Then you can use AMA PQ model to model your time series after differencing. Okay. So yeah, this yeah, we say the stationary for AR1 process, right? The phi1, the absolute value of phi1 is less than 1. And then if it is not than 1, for example, bigger than 1 means your time series is not stationary, right? It's non-stationary. So this is why we come up with this unit root test, right? And remember, the null hypothesis is you have a unit root, which is phi1 equal to 1. Okay, this phi1 equal to 1. And your alternative hypothesis is your phi1 less than 1. Okay. And then you will look at, yeah, this ADF test we discussed in seminar 4 also, right? So the null hypothesis is there is a unit root, right? And if there is a unit root, means your time series is non-stationary. And so you want to actually reject this ADF, right? They use ADF test. You want to reject this null hypothesis. So if the p-value is bigger than 0.05, that means you will not reject null hypothesis. That means your time series has a unit root. Then your time series is not stationary. Okay? Yeah. So if your time series is not stationary, and if you look at the line graph of your time series, you might consider using differencing, right, to remove the trend. So to ensure the time series after differencing is stationary. Okay. Yeah. So let's look at this activity. Uh, So we examine the stationarity of this time series, use SAF, PSAF, then construct the differencing or log transformation, right, of the series unit. It is until it is stationary. Okay, yeah, I give you 2 minutes to have a try. Okay, have a try. So you need to import the data, okay? So let me demonstrate the steps, okay? Let me demonstrate the steps. So let's import this ARIMA data, okay? ARIMA 2. Okay, let's import the data. Let's look at the data, a few columns. Here you can see we have 2 columns, right? We need to change the format of the first column, the date column, and convert it to time series. And also remember, you look at the series column, there are negative values, right? Negative values means you cannot do log transformation, right? Because they are negative, okay? Unless you shift all the data above 0. Otherwise, you cannot do a log transformation, okay? So let's convert the data, let's change the date and also convert it to a time series object. ARIMA 2 date. This is a year, months, day, okay? And ARIMA. Okay, yeah. So we convert this as a time series object. So let's look at the SAF and the PSAF. Okay, or you use just use TS explore function. You look at this line plot of your original time series. Clearly, there is trend, right? Downward trend, right? This downward decreasing trend. So it must be non-stationary, right? It must be non-stationary, and yeah, not normally distributed. And you look at the ACF, or if you want to maybe have lag equals to 24. Let's look at maybe 24. Okay. So ACF, you can see uh, not decreasing slowly, right? And not exponentially. There is clear indication of the trend in your time series, right? And look at your PSAF seems yeah, not a big problem. And but the ACF, right? You have decreased slowly, not exponentially, and there indicate it indicates there is clear trend. And if you look at the test, right, mean not zero, and they are not normally distributed, and they are not independent, right? And you can see the ADF test, stationarity test. So you will not reject the null hypothesis, means there is a root in your original time series, and your original time series is not stationary, right? Is not stationary. Okay, so you consider using difference, right? Okay, and if you look at the trend, if you look at the original time series, so maybe we can consider the first order difference. Okay, let's look at the first order difference. Okay, so let's generate a new column. Uh, Maybe the first order difference. Okay, and then let's look at maybe the series. Okay, ARIMA 2, the difference series. Okay, yeah. So we do a first order difference of the original time series, and let's look at the line plot. It seems quite okay, right? Quite okay. And normal distribution. And look at the maybe let's look at the lag. Let's increase the lag to 24. If you look at the ACF, you can see the ACF decreasing maybe very quickly, right? Very quickly, and only short-term correlation. Okay, and ACF seems you can say after leg three, leg two, you have a cutoff. Okay, you have cut off. And if you look at the PSAF, PSAF, and it seems there are no clear cutoff, because you can see from lag 5, 6, 7, 8, right? It's a big PSAF value. Okay. So here, and you also look at the test, right? And okay, the difference in series seems maybe have mean zero, and normally distributed, and stationary, because this p-value is less than 0.05, right? This ADF test. So it is stationary, and but it's not independent, right? They are dependent, they are correlated, right? This can be reflected by your ACF, right? ACF plot. So here you can see it's a stationary time series. Now you look at the ACF and PSAF of this first order differencing time series, you may consider this AR2 model, right? You may consider AR2 model, or you might consider maybe ARMA 11 model. Means you will use ARIMA 111 model, right, to model this time series. Okay, your original time series. Well, you can use ARIMA 111, right? Or you can consider use ARIMA 210, right? 210, right? To model your original time series. Okay. Yeah, so this is activity 5. I all be able to generate the same output as what I'm showing here. Okay, great. Yeah, great. Okay, yeah, very good. Yeah, that means you're still with me. Okay. Yeah, I know it's seminar 5, right? Some you have submitted your GBA and you may be very tired, right? And also for this course, the content is very heavy. Okay. So anyway, let's maybe yeah, try to do the practice. Okay. So we cannot use a log transformation for this time series because there are negative values, right? Okay, so basically here you can see it's not stationary and you have clear trend. And after first order differencing, it is stationary. And you can consider maybe a of ARIMA of not 210 model, right? Or you can consider ARIMA 111 model, okay, for your original time series. And then you select which model is better, right? Okay. Okay, so ARIMA PDQ model. Okay, ARIMA PDQ model, basically, remember, we will focus on the time series after differencing. Okay, for example, this after d order differencing. So you do difference in d times. Okay. Yeah, Sharifa, yes, it's a good question, very good question. And you look at the pattern of your original time series, right? If your original time series has a clear, maybe linear trend, you do a one order difference will be sufficient, right? If your original time series have maybe a similar quadratic pattern, quadratic trend, then you do two order differencing, okay? And there are very rare cases you do very high order differences because we say you may be over difference the original time series, and your over differencing will also create a problem, right? Because you will increase the variance of your time series after differencing, right? So you check. For example, this is my experience, right? You do first differencing, then you check the time series. If it is stationary, then you stop. And then if it is not stationary, you do second order differencing. And then check whether it is stationary. Right? This is actually do it step by step. There are no, so-called golden guidelines we can follow. Okay. Yeah. So sometimes it depends on your experience. First order or second order differencing sometimes is sufficient. In most cases, it will be sufficient to ensure the time series are stationary. No, it's not say something like if even after two order difference in your the time series is not is still non-stationary. It does not. Yeah, sometimes you can see some data you may have very unique patterns. For example, quadratic growth or quadratic decrease in sometimes those kind of pattern, right? So if even after two order difference, it is still not a stationary. You check whether maybe there are volatility issues, right? Or maybe some uh, underlying processes you need to understand. But it's not say your something is wrong with your data, right? If the data you collected follows the procedure, follows the steps, right? That should not you should not question about the data. Maybe some the way you collect data could be a problem, right? It's not about the data itself. Maybe how you collect data could be maybe some issues, right? So you need to go back and check. Okay. Yeah, it's a very good questions. Okay, very good questions means actually there are no golden rules. So how many differences you should proceed? Usually, first order, second order, in most cases, will be sufficient to ensure that the time series after differences is stationary. Yeah. All right, let's continue. Very good questions. Okay, yeah. So you can see, actually, we are working with the time series after differencing, right? For example, this after d-order differencing, right? After differencing, it is ARMA PQ model, right? So it is ARMA PDQ model, ARIMA PDQ model for your original time series, okay? Yeah, so this, we also have, what is this? ARMA 110. Okay, ARMA 110 means after first order differences, you have AR1 process, right? AR1 process. So you can see this is your process. So after this is first order difference, and it is AR1 process. So the original time series is ARIMA 110, okay, process. And so you can calculate the mean of this first order differencing time series and the variance of the first order differencing time series. Okay. And so the original time series, we say have no mean and a variance before differencing. Later we will discuss. Okay. There is a question. Yeah. Why a non-stationary process does not have any mean and variance? Maybe this question is not to save the time. Okay, so this question says non-stationary process will not have a stable mean and variance, and because they are non-stationary. Remember our definition of stationarity, right? In terms of the stationarity of time series, right? We say, of course, we focus on the weak stationarity, means the mean and the variance are constant, right? The mean and the variance are constant, okay? And for non-stationary process, usually you cannot have a mean or variance converge to some value, right? For example, let's look at this random work process. Okay, maybe a random work process without a drift. Okay, random work process. If you look at this random work process, you can see the mean of each in each period actually depends on the value in the previous period, right? Because this is a white noise. Mean zero follows the normal zero and a constant maybe variance, okay? Sigma square, okay? But the mean of yt, right, depends on the value in previous period, right? So we can say that will not converge to a certain value, right? And if you look at this variance, if we look at this variance and then you do this until you can see will be epsilon t plus epsilon t minus 1 plus epsilon t minus 2 plus and up to or epsilon maybe t minus infinity, right? That means in period t maybe up to epsilon 0. Okay, maybe let's say up to epsilon 0. So you can see there will be, and for each epsilon, it is normally distributed, right, with mean 0 and sigma square. So the variance of yt, you can see will be equal to t times epsilon square, right? The variance of yt, and depends on time. So this is why we say they don't have a constant mean or variance. So this is why we say we will transform or change the non-stationary time series to stationary so that we can apply the ARMA model, right? So this is the rationale behind for ARIMA model. We use the difference, right, to remove the trend and then make a stationary time series, and then we fit with the ARMA PQ model. Okay. All right, so this ARMA PQ model, we can use this TS ARIMA function, right? Specify with the orders, and then you specify whether you want to include a constant in your model, okay? And then you look at the output from R, and you should be able to write down the model. Here it is ARIMA 110 model, means after just one order difference, right? So the time series will be nebula YT, right? Nebula YT, and then the constant, okay? Constant is this guy. And then you look at the AR coefficient, and this is phi times this AR1 term, and plus epsilon t, okay? And of course, you can calculate this intercept, okay? This intercept, which is the mean of this differencing time series, nebula YT, right? Nebula YT. Okay, yeah, then we can perform the evaluation of the model in terms of AIC, BIC criteria, and you also evaluate the residuals, whether the residuals follows white noise process, right? If the residuals follows white noise process, means your ARIMA model captures or extract the information from your time series. Okay, so let's look at this activity. Fit an ARIMA model on the variable series in that, evaluate the fitted model. Okay, yeah, so let's go back. Let's go to the R, okay. So after first order differencing, you can see the time series becomes stationary, right? Because you look at the test. If you look at the test, and after first order difference, and it is a stationary time series, and then we can perform ARMA model, right? We can perform ARMA model. And if you look at the ACF, if you look at the ACF, and we say after two legs, leg 2, right? Leg 2, there is a cutoff. So you can consider MA2 process, right? For this time series after differencing, right? And here, if you look at the PACF, and so it's not, there is no clear cutoff, right? Even after leg 6, right? So we can try with MA2 for the differencing time series, okay? So let's fit the time series, the original time series, with ARIMA 012, right? Because we can focus on the first order differencing time series, and this MA2 model can be fitted based on the ACF plot, right? So we can fit this model with ARIMA 012 model, okay? So let's do this, okay? Or we can consider different models. Maybe this is one model, right? ARIMA 012. And you might also consider, for example, you look at the PACF, you want to see maybe after, yeah, you can consider maybe ARMA 11 for the difference in time series, or ARMA maybe 21. Okay, so let's try with different models. Okay, let's try with different models, and then select the best, maybe most appropriate one. Okay. Let's consider ARIMA 211, okay? ARIMA 211 model. And let's also consider ARIMA, maybe I just copy. ARIMA maybe 112, okay? 112 model. And let's also consider ARIMA maybe 012 model, right? Based on the PSAF, okay? And let's consider these three models. And then we compare which model maybe is the best, okay? So let's consider if we look at this ARIMA 211 model, the AR term is not significant, right? On the other two term, AR1 model, AR1 term is not significant, but the other two terms are significant. And look at the AIC or BIC and BIC, right? And then look at ARIMA 112, and the AR1 term is not significant, and the AIC and BIC decreases, right? So ARIMA 112 is better than ARIMA 211, right? And then look at ARIMA 012. Okay, ARIMA 012, if you look at the two terms, right? The MA terms, they are significant, right? They are significant. And also you look at the AIC and BIC, and these two values are also smaller than ARIMA 112. So for this case, we will be confident to say that ARIMA 1012 is the best model among the three, right? So we can finally determine that we use ARIMA 012 to model our original time series, okay? So let's generate this model, okay? ARIMA 012, okay? So 012 and include constant true. Let's okay, summarize the model, and let's check the residuals. Check the residuals of, if the residuals are white noise process, that means this model is a good model, okay? All right, so this is ARIMA. We finally choose the ARIMA 012 model, right? Based on the comparison among different models, and also look at the PSAF of your first order differencing time series, okay? And you look at the residual plot, seems good. And the residuals maybe seems along the 45-degree line, and QQ plot indicate that residuals follow normal distribution, and SAF of the residuals you can see after like 0 means all can be considered as 0 SAF. And PSAF, you look at the PSAF, all within 2 standard deviation, right? That can be considered as 0. And look at the test, right? So the residuals mean 0 supported, normal distribution supported, and stationary supported, and independent supported, right? So the residuals are white noise, right? You can say the residuals are white noise process. So the ARIMA 012 model extract the information from your original time series, and it is a good model, right, to fit this data. Okay. All right. Are you all with me now? Do you have any questions? Okay, great. Yeah. So some of you responded in the chat box. Okay, I'm happy to see that still with me. Okay. All right. So you can see we can use ARIMA 012 model, right, to capture this process. All right. So let's go back to the slides. Okay, so forecasting. Forecasting, remember, you are work ARIMA model, and if the difference is not zero, the D is not zero means you are working with the differencing time series. And do remember you are working on the differencing time series, and the differencing time series is ARMA-PQ model. And then you need to do a additional step, right? And get back to your forecast. Okay, this is the forecast for your original time series. Okay, and for example, this two step ahead. This ARIMA 110 means the first order differencing process is AR1 process, and then you go back, and eventually you can see it is recursive, and you need to substitute the previous forecast into this forecast equation. Okay. And yeah, for each step forecast, right? Each step forecast, and so it is recursive equations, and you will do that step by step to get the forecast. Okay. And okay, of course, when you do the forecast, and the R will also help you to get the confidence interval of your forecast. Okay, confidence interval of your forecast. And so this is an example to illustrate the forecasting process with ARIMA 110 model. Okay, and so basically you focus on the differencing this time series, and it follows on AR1 process. So this column is AR1 process, right? This column is AR1 process. And then you need to go back to your original time series to get the forecast, right? Okay. So I will not explain these slides. So you can, yeah, you can use the TS forecast function, right, to do the forecast. And this is your RINMA model and the number of steps you want to do the forecast, and you plot the forecasted value, all right? So let's go to activity 5.7, okay, 5.7. Now remember this time series is monthly data, okay, monthly data, you calculate 12 months forecast. So basically 12 steps, right, 12 step ahead of forecast, okay? And then plot the forecast value. So it is quite straightforward, okay? So we have determined the model, which is ARIMA 012 model, right, for the original time series. And then we just use the TS forecast to get the forecasted value for the next 12 period. Okay, so we just use TS forecast. And this ARIMA 2, ARIMA, this your model, and 12 period ahead forecast, and then forecast include, you want to plot just the forecasted value, okay, forecasted value. So this is your forecast for the next 12 period, okay, for the next 12 period. And you can see you have confidence interval, and the confidence interval becomes bigger when your number of steps for forecast increases, because it becomes less accurate, right? with more time ahead of forecast. Okay. All right, so this is a forecast. Let's go back. Okay, so do a quick summary. So this integrate part actually is a difference, right? And depending on how many order of the difference you need, right, to ensure that your time series after d order difference is stationary, right? You need to ensure after d order difference you have a stationary time series. And so for any the difference series will be have the same property as any other stationary AMA process, right? So you can identify the order can be identified by ACF, PSAF, right? If you observe clear cutoff for the different time series, and for example, in terms of ACF, right, you consider MA process, right? And if there is clear cutoff in terms of PSAF after certain legs for the different time series, you consider AR process, okay? And if both have no clear cutoff and but decrease exponentially, right? You consider maybe AMA 11, AMA 21, AMA 12, right? Process, okay? And okay, okay, when you do forecast, okay, you must revert back because you are working on the difference time series, right? After the order difference, and then you need to revert back, okay? And for high difference in orders, it will becomes much more complex, okay? Okay, so last topic we discuss the seasonal, okay, ARIMA model, okay? The SARIMA, okay, seasonal ARIMA model, SARIMA models, okay. So we also consider the seasonalities of the time series, okay. So look at this data. So basically, the seasonal ARIMA model or SARIMA model, I forecast future values based on ARIMA concept with consideration of series seasonality. Okay, so let's look at this quarterly data. Quarterly data. So the seasonal cycle will be 4. Okay, will be 4, and so this example, so we will see clear seasonality effects because if you look at, for example, the data in second quarter, right? And the data is always the highest among the same year. For example, in 2023, second quarter, this data is the largest. And in 2024, quarter two, the data is the largest. And similarly, in each year, the fourth quarter, the number is the smallest, right? The number is the smallest. So you can clearly see this seasonality effect in your data, okay? So this seasonality effect. So for example, uh, if this you want to forecast, for example, first quarter in 2024, so basically this will be affected by the previous period and also the previous the same season in previous year, in previous seasonal cycle, right? So this is seasonality, right? So when you forecast, for example, the value in 2024 Q1, and this number will be affected by the previous period, right? Or maybe the previous 2 period, or even previous 3 periods, due to these short-term correlations, right? But also be affected by the same seasonality impact in first quarter in Q1, right? So this what do we mean here? So this the forecast for Q1 2024 may take maybe observe values of forecasting errors of both Q1 2023, the same season in the previous cycle, and maybe the most recent period, right? Okay, so we need to model this Sarima model, right? To get the parameters of the model. So here we use Sarima PDQ and smaller PDQ, okay, and then those capital letters, okay, capital letters PDQ, okay, and L refers to the seasonal cycle length. Okay, how for example, for quarterly data, this L will be 4, right? So your length of seasons, each seasonal cycle will be 4, and for monthly data will be 12, and for weekly data, maybe 52. Okay, and so this the length L refers to the seasonal cycle length. Okay, and this Arima PDQ, Sarima PDQ, and PDQ model, right? So this is quite complicated, right? So now let's look at this uh, Arima PDQ. Okay, Arima PDQ actually means there are no seasonal effect in your model, right? So that means this capital PDQ will be all 0, and the seasonal cycle length will be 1. Okay, seasonal cycle length will be 1. So this is Arima PDQ, and if you write it as a Sarima model, right? Sarima model, this will be PDQ 001. Okay. If you have ARMA PQ model, ARMA PQ model basically is ARIMA P0Q, right? ARIMA P0Q and no seasonal. So 00 and cycle length 1. Okay, right in Sarima in this way. And if you have if you have an ARP model, ARP model itself is ARIMA P00 and no seasonal. Okay, 0, and 1. Okay, or MIQ model, right? MIQ model is ARIMA 00Q, and then no seasonal. So you write in Sarima, then you put 3 zeros and cycle length 1. Okay, so this is the notation of the various models. It becomes much complicated, right? Okay, so this is what we mean here. Okay. So let's look at activity 3.8. Okay, 3.8, 5.8. Okay. Uh, the total, okay, the total series in arrival and then do log transform as well as difference, right, to one order difference, and then examine the SAF, PSAF, and compare them with SAF, PSAF of the original, okay, original time series. Discuss what you observe here and whether future further transformation difference is still required. Okay. All right. I give you maybe 2 minutes to import the data. Okay. Import data into R. All right. So let's do it together. Okay. Let's do it together. So let's import the arrival data, which is arrivals. Remember, we have I think here you can see the date column, we need to change the format. And we need to rename this total arrivals column and then convert it to a time series object. Okay. Let's first change the name of the second column. Okay. And let's change the date. Okay. Okay. Let's convert the second column. Maybe. Okay. Yeah, so we convert the second column into a time series object. Let's look at. All right, yeah. So we have this data preparation done. Okay, so let's look at the original time series, the total column. Okay. Okay, so maybe let's lag equal to this is monthly data. Okay, monthly data that could be seasonalities. Okay, seasonalities. So let's maybe make seasonal cycle will be 12. Okay, so let's maybe use lag 48. Okay, so if you look at the original time series, it has a clear trend, right? Maybe this quadratic trend, right? Quadratic trend, right? And maybe you consider use two order difference, right? Difference to get a stationary time series. And the original, if you look at the ACF, and clearly it has a trend in your original time series because the ACF does not decrease exponentially, just slowly, right? Indicate long term these correlations. And if you look at the PICF, if you look at the PICF, you can see there are peaks for certain periods, right? For example, this 12 lag, right? 12 lag, and then there are some peaks for few lags, okay, and then so this indicates there are clear seasonalities, right? Because you can see uh, when the lag is 1 and the lag is 13, right? And then the PSF is very big, okay, very big. And so you will consider maybe just using difference to remove the trend might not be sufficient, right? That could be seasonalities in your time series, especially when you look at the PSAF, right? The partial autocorrelation function. And then there are peaks after regular legs, right? So there could be a seasonality of your data. All right, so this is the original time series. So let's do maybe the first order difference. Okay, let's do the first order difference. Okay. Let's do the first order difference. Okay. So we do the first order differencing of the total of time series, original total time series. Let's look at the first order differencing time series. Okay. Okay. So this is the first order differencing. Let's look at the PSAF, SAF, and the PSAF. Now this is a line plot. And for the line plot, you can see the trend has been removed, but seems the volatility, right, becomes bigger and bigger when the time increases. Okay, and not normally distributed. And if you look at the ACF, okay, if you look at ACF, there are clear patterns, right? So the ACF, uh, leg 0, leg 12, you can see they are very big. And those legs decreases. You can see the leg 0, leg 12, leg 24. Those uh, series, those ACF decrease slowly, right? Slowly, not exponentially, right? Decrease slowly, right? For regular legs, okay? Regular interval of the leg. And then if you look at the PSAF, there are similar, there are some also very uh, uh, significant pattern, right? For the PSAF, and for example, in some of the legs is very big, leg 11, leg 12, this quite big, and then leg 24, also a big number, right? And then this maybe leg 36, also big, right? So these are indications of seasonalities of your data, right? If you look at the difference in time series, although the difference you can see, okay, they are with mean zero, but not normally distributed, and they are stationary, and they are not independent, right? Although this is stationary, but there are clear seasonalities based on ACF and PSAF, right? Okay, so we can consider the seasonal difference. Okay, if you look at the ACF, if you look at the ACF, and for every 12 period, you can see this ACF 10, 11, 12, every 12 period, the ACF decreases slowly and quite big, right? So we may have a seasonal difference with the seasonal cycle length equal to 12. And remember, it is actually it's a monthly data, right? So the seasonal cycle will be 12. Okay, so let's do it. Let's get the uh, seasonal difference in series. Okay, let's first uh, let's name this as D1. So you do first order difference of your original data, and then you based on this difference data, you do a seasonal difference. Okay, then we use this TSD function. So arrivals total, your original time series, and we will have additional two parameters. Order equal to 1 means you first do the first order difference in your original this total time series, okay, arrival total, and then another parameter which is order dot d equals 1. Okay, this means this is a seasonal difference. And then if you do not specify the seasonal length, the data, the function will uh, uh, by default using the frequency of the data. That means for this time series, because it is monthly data, so it will treat the seasonal length cycle as 12. Okay. So this we will have a new column in the arrivals time series data set. And this we first do this first order difference. And then for the first order, after the first order difference, we do a seasonal difference with just uh, with seasonal cycles of 12. Okay. Okay, so if you are not sure about the TSD function, you can just look at the explanations. Okay, you can look at the explanation of this function. Okay, so this function you can say TSD function. So your time series, okay, this by default lag will be one, order will be one, and this seasonal difference lag will be zero. And if you do not specify that, so it means uh, the R will use the frequency of the series for this parameter, right? Which means for our monthly time series, it will be 12. The seasonal cycle will be 12, okay? And this order dot D, this is a seasonal difference, okay? And you can say default is 0, so you need to specify that as 1, okay? Means you will do a seasonal difference, okay, with order 1, and the seasonal length cycle is 12 for this data set, okay? Okay, so we have this, let me remove this, okay. So we look at the first order difference and the seasonal difference after seasonal difference, okay. Okay, so this is we do two differencing, two-step difference. The first is first order difference on original time series. And then based on the difference time series, we do the seasonal difference, okay, with seasonal cycle length, which is 12. And then you look at the SAF and PSAF. Okay, maybe we say lag 248. Here you after you do the seasonal difference, you can see the ACF. Uh, it seems becomes more regular, right, for a stationary time series. And you look at the test of this time series, and the mean is 0 supported, and not normally distributed but stationary, and not independent. So it's a stationary time series, and we can use AMA model, right, to model this time series. Okay, so basically it's a Sarima model. Okay, here you look at the PSAF. Still there are peaks, right? But we can try with Sarima to Arima models with seasonality. Okay. So this is activity 5.8. I need to be a little fast. Okay. Okay. So you can see if you look at the data, okay, then the ACF have decreased slowly for certain the same legs, right? Leg 4, leg 8, leg 12. So for this is a quarterly data, and seasonality, the seasonal cycle is 4, and you can consider there a seasonal impact, okay? And the typical SAF was with seasonality, this SAF, and you can see uh, uh, the same leg, right? Leg 4, leg 8, leg 12, and the SAF, PSF decrease slowly. Okay, so it's a typical pattern for data with seasonality. Okay. Okay, so for example, is if the seasonal cycle is 4, right? Seasonal cycle is 4, and the ACF has cut off at 4 legs, and the PSAF have cut off decays at legs 4, 8, and 12, and so we can say it is a seasonal MA model, right? Because ACF has cut off after season 4, right? And then so it's a seasonal impact effect in your time series, and it is a MA model. Okay, so it's a SMA one model, right? Because the seasonal cycle is 4. Okay, L equals 4. And similarly, if your ACF is exponential decaying every L legs, while PSF have cut off at after P cycles, then you will consider SAR model, right? SAR model, okay? So no MA terms, so seasonal with AR model, okay? If both PSAF and SAF are exponentially decreasing, so it's seasonal AMA process, right? So decreasing exponentially for ACF and PSF, and then you can consider a seasonal AMA model. Okay, and if ACF decays very slowly every L legs, and so you need to consider the conduct a seasonal difference, right? Because that decreases very slowly for every regular L legs, right? 4, 8, 12, right? This kind of thing. So you need to do a seasonal difference. Okay. So the Sarima PDQ and PDQL process is very complicated. Okay, very complicated. And so we will denote that L refers to the seasonal cycle length. Okay, seasonal cycle length for monthly data 12, weekly data maybe 52, quarterly data L equal to 4. Okay, and so this is very complicated. Usually, these Sarima orders, if you have orders bigger than 2, it's very, very complicated. Okay. So let's look at very simple examples. Sarima 00 and this uh, 10012 process. Okay, so basically you can see this is a seasonal model with cycle length 12, and the smaller PDQs are 0 and the DQ are 0. So it is a seasonal AR1 process, right? Seasonal AR1 process. Okay, so and the seasonal cycle is 12. And of course, you can get the mean and the variance. Okay, and the stationarity depends on this capital phi, right? Phi one is within 1. Okay, and the ACF or PSF of this Sarima 00 or this seasonal AR1 process, and this is typical characteristics. You can see the original time series. You will have ACF decrease slowly for every 12 leg, and because the cycle length is 12, right? But the PSF after leg 12, you can see after leg 12, and they have cut off. Okay, so this is the typical characteristics, okay, of Sarima or this seasonal AR1 process. Okay, and we can use this, but you need to use seasonal, this additional parameters you need to specify in this TS ARIMA function. Okay, and this is, you can see this is a seasonal AR1 process with cycle 12. Okay, cycle length 12, and then you can write down this model because this cycle length is 12. So, and this is a seasonal AR1 process. So this is the model, right? And this is AR1 process. Okay. All right, so forecasting. Okay, forecasting with this is also very complicated sometimes. Even if for this seasonal AR1 process with cycle length 12, seasonal cycle length 12, so it is also very complicated. Okay, and uh, for example, you want to do a one-step forecast, and then you will use this t minus 11, right? T plus 1 and t minus 11, right? So you can see you must be careful when you do the forecasting. Okay. All right. So this is a general forecasting formula. Okay. Yeah, this is an example. It's just an example. Basically, you fit this Sarima 00100012 model, okay? And it is a seasonal AR1 process with cycle length 12, okay? And yeah. All right, so we can use the TS forecast to do the forecast after you fit the model with Sarima, right? Sarima model to fit your data. Okay, let's do the final. No, not final. Uh, Look at the non-seasonal Sarima model, seasonal and non-seasonal Sarima model for series in arrival. Okay, let's go back. Let's go to this. Let's look at this. So here you can see we have a seasonality, right? So after first order difference, we still observe typical patterns of ACF and PSF. So we consider there are seasonalities, right? There are seasonalities in this data set. So basically you can consider the seasonal cycle will be 12, and you can consider uh, lower order Sarima models. For example, Sarima 011, 111 model, something like that. Okay, and you might consider Sarima for the seasonal part. Consider uh, uh, seasonal 011, right? And maybe 110 and 011 something. Basically, you can try with different Sarima models and then determine which one is the best on the maybe information criteria, and also the residuals. Okay, the residuals. Okay. So we will compare different models in activity 10, last activity. Yeah, last activity. Okay, so basically let's consider different Sarima models for this time series. Okay, so it's quite complicated. So you will try with a different Sarima model. So let's try with Sarima arrivals, your original, okay, the original time series, and this order is Arima mod order. That's with 0, 1, 1, and seasonal, okay, maybe 1, 1, 1, and include constant true. Okay, so let's try play with a different Sarima model. Okay, so maybe we can try 011 with a seasonal this 011. Okay, maybe we can try with odd Arima order will be 110. Okay, 110, and a seasonal will be 1102. Okay, we try with four different. Okay, let's try with four different. 111 with 011. Okay. Okay, so you try with a different Sarima model, and then you look at the maybe the p-value of the terms in your model, and also the AIC, BIC information criteria, and you will look at this one. So eventually, which model I select? Okay, I'll look at the model I select. 011, 011. Okay. Yeah, you look at the 011 model with cyclines 12. Okay, AIC is this number, similar to 01111 model, right? But the BIC is smaller. Okay, BIC is smaller. Okay, and then you compare with another Sarima model. You look at it, it become bigger, right? This AIC become bigger, BIC also become bigger, and this AIC becomes bigger, also bigger, right? Yeah, and then BIC becomes bigger. So maybe you will select this Sarima 011 This will be your choice, okay, to fit this data. Okay, suppose we use Sarima 011. Okay, 011. So let's so we say Ravel 2 to Sarima. Okay, and let's explore the residuals. Okay, something is wrong. Okay, this Sarima. Okay, residual. Okay, forgot a residual. Okay, so you will check the residuals and look at the residual ICF and PSAF. Seems okay, right? And then you look at the test, right? So mean zero and but not normally distributed. It's stationary and it is independent, right? And actually, yes, it's not normally distributed if you look at the QQ plot of your residuals, right? So, but anyway, this model captures most of the information from your original time series. Okay, and then you do maybe 1 year forecast. Okay, so this is the 1 year forecast. Okay, so yeah, so you can see it's very complicated for Sarima models, right? Uh, yeah, I think this is all what we have for today. I'm sorry we have a few minutes delay, 4 minutes delay now. Okay, so basically you can see we integrate both ARIMA models with seasonality. And do remember we are working on the differencing time series. All right, and so we consider this Sarima models, and Sarima model considers both in additive multiplicative time series can fit with the seasonality effect. Okay, and it sometimes okay you may try with different Sarima models and select the best, right, the best one. And of course, it depends on sometimes depends on your objective of your study with the time series. And remember, the simpler model, the better, right? The fewer parameters in your model, the better. So as long as the model can capture most of the information from your original time series, then the better. Okay. All right, so this is all for today. I'm sorry we have a few minutes delay. And let me know if you have any questions. And so for the Sarima model, yes, it is complicated, right? Even the Arima model is becomes complicated, right? And so sometimes you need to do, especially when you are dealing with time series, you need to try with different models, right, based on different criteria, and then finally select the best, maybe the most appropriate model, right, among a few alternatives, and then continue with your analysis and forecast. All right. Okay, this is all for today. Sorry for 5 minutes delay, and let me know if you have any questions. And if you don't have, and enjoy your evening. Okay, great. Yeah.